And to understand the Raptor 3, one must view it not as a static assembly of parts, but as a high-bandwidth thermodynamic transaction. In the previous discussion of the melting point problem, we established that the engine operates in a thermal environment that would liquefy its own structure in milliseconds. The solution to this existential threat is an engineering feedback loop known as regenerative cooling. This is the closed-loop circulatory system of the rocket, a process where the propellant, in its cryogenic state, acts as a sacrificial heat absorber before it ever fulfills its primary role as a source of thrust. And in the Raptor 3, this is not merely a cooling strategy. It is an energy recovery mechanism that elevates the engine's efficiency to the theoretical limits of physics. In the biological metaphor, the engine's bloodstream. For a systems engineer, the most intuitive way to visualize regenerative cooling is to compare it to the thermoregulation of a high-performance biological organism. Consider the human body during intense physical exertion. As the muscles, the combustion chamber, generate heat, the vascular system, the cooling channels, dilates to increase blood flow to the surface. This blood absorbs the heat and carries it away to be dissipated. And in the Raptor 3, the blood is liquid methane, stored at approximately negative 160 degrees Celsius. Before this, methane is injected into the preburners, or the main combustion chamber. It is routed through a labyrinthine network of thousands of microchannels milled directly into the chamber walls. This is a cold start architecture. The methane enters the base of the nozzle at cryogenic temperatures, racing upward toward the injector head. As it travels, it steals the thermal energy that is attempting to migrate from the 3,300 degrees Celsius combustion zone into the metal lattice. And this creates a spectacular paradox. The very fluid that will eventually create the heat is first used to prevent that heat from destroying the machine. This is the ultimate pre-processing step. In the same way a software engineer might use a sandbox or an input validation routine to ensure a packet of data won't crash the system, the Raptor 3 uses its fuel to validate the thermal environment of the hardware before the main execution, or combustion, occurs. And the thermodynamic bonus, turning waste into work. In a traditional open-cycle engine, heat lost through the chamber walls is considered parasitic loss energy that escapes the system without contributing to thrust. However, the Raptor 3 full-flow, staged combustion cycle turns this loss into a gain. This is where the concept of regeneration earns its name. And as the cryogenic methane flows through the chamber walls, it undergoes a phase change. It absorbs so much energy that it transitions from a subcooled liquid to a high-pressure, supercritical gas. By the time the methane reaches the turbopump turbines and eventually the combustion chamber, it is significantly more energetic than it was in the tank. And from a graduate-level perspective, this is an enthalpy boost. We are increasing the internal energy of the propellant using waste heat that would otherwise be discarded. This preheated fuel requires less chemical energy to reach its ignition threshold and expands more violently upon combustion. In this sense, the cooling channels act as a secondary heat exchanger, pre-burning the fuel using the heat of the main chamber. It is a masterpiece of energy recycling. The heat that threatens the engine's life is captured, packaged, and fed back into the system to increase the total specific impulse, or I sub SP. An architecture of the cooling channels, the micro-scale frontier. The physical implementation of this system is a marvel of additive manufacturing and precision milling. If you were to slice a Raptor 3 combustion chamber in half, you would not see a solid wall. Instead, you would see a cross-section resembling a honeycomb or a high-density radiator. And these channels are not uniform. Because the heat flux, the rate of heat transfer, varies wildly at different points in the engine, the cooling geometry must be equally variable. At the throat of the engine, the narrowest point where the gas velocity reaches Mach 1, the heat flux is at its absolute peak. Here, the cooling channels must be thinner, the flow velocity of the methane must be higher, and the fin efficiency of the channel walls must be optimized to the decimal point. And for the computer scientist, this is a load balancing problem. If the methane flows too slowly through a high heat zone, it will film boil, forming a pocket of gas that acts as an insulator, preventing further cooling and leading to an instant hot spot and structural failure. If it flows too fast, the pressure drop across the cooling jacket becomes too high, taxing the turbopumps and reducing overall engine efficiency. The Raptor 3 cooling jacket is essentially a hard-coded algorithm in metal, designed to balance mass flow, pressure drop, and thermal absorption in real time. In the boundary layer, the kinetic buffer, while regenerative cooling handles the heat that has already entered the metal. The Raptor 3 employs a second, more subtle defense mechanism to prevent the heat from reaching the metal in the first place. This is the boundary layer, a fluid dynamics phenomenon that acts as an invisible, sacrificial shield. And to visualize this, imagine moving your hand quickly through a candle flame. You don't get burned because a thin layer of air molecules remains trapped against your skin, acting as a momentary insulator. In the Raptor number 3, this principle is weaponized. And the injector plate is designed to overfuel the perimeter of the combustion chamber. By injecting a slightly cooler, fuel-rich mixture along the inner diameter of the wall, engineers create a buffer zone. This boundary layer gas is significantly slower and cooler than the raging, supersonic core flow in the center of the chamber. And in the language of computational fluid dynamics, we are managing the stagnation temperature at the wall. If the 3,300 degrees Celsius core gas were allowed to touch the copper liner directly, no amount of regenerative cooling could save it. The boundary layer acts as a thermal resistance, or R value in the circuit. It forces the heat to move via conduction through a gas layer before it can reach the metal, drastically reducing the heat flux that the regenerative system has to handle. And for the graduate reader, this is analogous to thermal throttling in a CPU. Just as a processor might lower its clock speed to keep its internal temperature below the T-junction limit, the Raptor number 3 uses the boundary layer to throttle the amount of energy that reaches its structural components. It is a software-defined layer of protection, where the software is the precision-drilled pattern of the injector face. In the pressure paradox, cooling under stress, one of the most difficult aspects of the Raptor 3 cooling system is the extreme pressure differential. The combustion chamber operates at upwards of 350 bar over 5,000 psi. To force the cooling methane through the walls and into the chamber, the pressure inside the cooling channels must be even higher, often exceeding 500 or 600 bar. And this creates a pressure sandwich. The thin walls of the cooling channels are being squeezed from the outside by the structural jacket and from the inside by the cryogenic propellant, all while being softened by the intense heat of the combustion. And this is where the regenerative aspect becomes a structural challenge. The metal must be thin enough to allow heat to pass through quickly, which is high thermal conductivity, but strong enough to withstand the delta P, or pressure difference, between the cooling channel and the combustion zone. If the wall is too thick, the thermal gradient across the metal becomes too steep, and the hot side of the metal will melt while the cold side remains chilled. This is known as thermal stress cracking. And SpaceX solves this by using the closed-loop nature of the FFSC cycle. Because the entire engine is pressurized, the pressure difference across the internal walls is minimized compared to simpler engine cycles. However, the margin for error remains razor-thin. A single microscopic blockage in a cooling channel, essentially a bit flip in the hardware, would lead to a localized overheat, a burn-through, and the catastrophic loss of the engine. And the dry engine advantage. It is important to note that the Raptor 3 is a gas-to-gas engine. In older engines like the Saturn V's F1 or the Falcon 9 Merlin, the propellants are injected as liquids. These liquids take time to atomize and evaporate, which creates a chaotic and somewhat dirty thermal environment. In the Raptor 3, by contrast, injects its propellants as hot, high-pressure gases thanks to the pre-burners. This makes the combustion much more uniform and predictable. For the cooling system, this is a double-edged sword. On one hand, the steady state of the gas-to-gas combustion reduces the likelihood of combustion instability, the violent pressure oscillations that can scrub away the protective boundary layer. On the other hand, gas-to-gas combustion is much hotter and more efficient, meaning the thermal load is more concentrated. And the regenerative system must therefore be more responsive. In the Raptor 3, there is almost no thermal inertia. The system is so finely tuned that any change in engine throttle must be met with an instantaneous and precise change in cooling flow. This is real-time systems integration at its most extreme. The flight computer doesn't just set a throttle level. It manages a complex multivariable matrix where cooling capacity is the primary constraint on thrust output. And failure modes when the loop breaks. What happens when the regenerative loop fails? In the aerospace industry, this is colloquially known as engine-rich exhaust. And if the cooling flow is interrupted, perhaps due to a pump cavitation or a transient pressure spike, the regenerative cycle flips from a virtuous cycle to a vicious cycle. Without the methane to carry the heat away, the copper liner reaches its melting point in microseconds. The 350 bar of internal pressure then forces the molten metal into the combustion stream. The green flash often seen in rocket engine failures is the signature of the copper liner being vaporized and burned. And this is the hardware exception that SpaceX engineers work tirelessly to catch. The Raptor 3 is equipped with an array of sensors that monitor the health of the regenerative loop. If the delta T, or temperature change, across the cooling jacket deviates from the predicted model, the engine's control logic can initiate an emergency shutdown before the structural integrity is compromised. It is error handling at 30,000 RPM. And the limits of regeneration, as we look toward the future of the Raptor 3 and its role in the Starship system, we must acknowledge that regenerative cooling has a saturation point. There is only so much heat a given mass of methane can absorb before it becomes too hot to be an effective coolant. And SpaceX is constantly pushing this saturation point. By refining the chemistry of the alloys and the geometry of the channels, they are squeezing every possible joule of cooling capacity out of the methane. But as chamber pressures continue to climb toward 400 bar and beyond, the regenerative system alone may not be enough. And this brings us to the final piece of the thermal puzzle. While the regenerative loop provides the primary defense and the boundary layer provides the secondary shield, the material science of the engine provides the ground truth. To truly master the heat of the Raptor 3, SpaceX couldn't just rely on clever plumbing. They had to invent new materials that could survive where all other alloys failed. And the regenerative system is the process that manages the heat, but the superalloys are the substrate that makes that process possible. To understand how the Raptor 3 bridges the gap between liquid and solid in such a violent environment, we must examine the proprietary metallurgy that forms the backbone of the engine. And the mastery of regenerative cooling transforms the Raptor 3 from a mere burner of fuel into a sophisticated thermal management system. By treating the cryogenic methane as both a coolant and a propellant, SpaceX has created a zero-waste thermodynamic cycle that thrives on the very heat that should destroy it. However, even the most perfect cooling loop is only as strong as the metal that contains it. This necessitates a leap into the world of advanced metallurgy, leading us to Section 5.3, SpaceX Superalloys, SX500, and the quest for heat resistance.